Introduce your lecturer for today, Jussi Enkovaara. Is that correct?
Yes,
that's the
more
right
or less.
Enkovaara is a senior application scientist in high-performance computing at CSC IT Center for Science in Finland. He received his PhD in computational physics in 2003 from the Helsinki University of Technology. He's worked as a postdoc researcher in Research Center UH, Germany, and started at CSC in 2005. His scientific background is in electronic structure calculations for condensed matter systems. I don't know what that means. Current research interests include development of massively parallel methods for density functional theory and time-dependent density functional theory-based simulations. Jussi is your lecturer. Let me introduce to you the trainers. You have Jussi sitting in the back. Matti raises his hand, and there should be someone named Jonathan who isn't here yet. He has a ponytail, but those are your three trainers who will help you with anything that you need help with, because there's a lot of people here. There will be more people trickling in during the course of the day. Good luck, and I'll see you at 6 o'clock.
Okay, thank you.
Sure.
Thank you for the introduction, and it's really nice to be first time in Israel. Yesterday, you had some lectures about basic usage of message passing interface and how to do parallel programming with MPI. Today I will discuss some a bit more advanced topics. We start with a thing called user-defined data types, which allow one to send non-contiguous segments of memory. The schedule is more or less following. We have first about 1 hour of lectures, followed by about one hour of hands-on exercises. You should be able to download some exercise material from the course web page. Then we have the coffee break, continue with another hour of lectures. This time we'll discuss mainly parallel input and output using MPI, and once again followed by about 1 hour of exercises. And after lunch, we'll discuss shared memory programming with OpenMP, as well as hybrid programming with OpenMP and MPI. Just to get started, how many of you have been doing any MPI programming before yesterday, let's say? Okay, so you should have some experience. Also, out of curiosity, how many of you are programming in Fortran? And the rest of you are programming in C, right? Yeah. My lectures will be mostly bilingual. And also for the exercises, you can do with them both in Fortran or in C. Some of my demos I will be showing in C, some in Fortran, but I think you should be able to easily follow, even if that's not the language of choice for you. As Hank nicely introduced, I work as application scientist at CSC, the Finnish Supercomputing Center, and I've been doing high-performance computing, parallel programming more than 10 years, and used various systems ranging from simple Linux clusters to supercomputers. I think the biggest sort of benchmark runs I've been doing have been with over 100,000 CPU cores, and quite routinely I'm doing some benchmarking and sometimes also production calculations with thousands of CPU cores. Okay, but let's get started with user-defined data types. As you learned yesterday, when you're communicating something with MPI, when you're sending and receiving messages, you have to specify the sort of type of data you are communicating. And with MPI, you have to use these MPI's own data types. One reason why you actually cannot use just C's, ints, floats, doubles, or equivalent Fortran constructs is that MPI has basically been designed so that it can work also in heterogeneous environments where the size of the data types in different MPI processes can be different. And one way to think about these MPI data types is that they always tell you where to take the data when sending, how many bytes to take, and in which kind of order take the bytes. And similar when receiving, how many bytes you should take and how they should be interpreted. In principle, you can think that when you are passing the actual send-or-receive buffer to the MPI, you're always just passing some memory address, and then the MPI data type tells that how you should be accessing this memory location when sending and receiving. The elementary data types, MPI int reals, they can be used only for communicating contiguous segments of memory or sequence of identical elements. But as we'll discuss shortly, there are quite few cases where one might want to actually communicate non-contiguous segments of memory, or sometimes even non-identical elements, for example, structures or so, would see your structure in Fortran. One simple example about situation where this kind of non-contiguous communication patterns might arise is that let's say we are now working with Fortran and we have some matrix there and we would like to send one row of this matrix. In Fortran, if this is our original matrix, Fortran uses so-called column major ordering, which means that when we look how the data here is arranged in computer memory, in principle, computer memory is always just a linear segment of memory, while the actual logical layout for your array in this particular case is two-dimensional. The column major ordering means here that when we are storing this array in memory, we first store the first column, like this one. Then we store the second column, and finally the third column, like this one here. If we would be using C, C uses so-called row major ordering, and in C case it would be actually the first row here, second row here, and third row here. Now, if in Fortran we actually want to communicate this first row here, because of this column major ordering, the first element of this row is located here, but the second one is actually, it's not next to here. There is some stride between there because of the column major ordering. And same for the third one here. So the sort of memory pattern we would like to send or receive is not contiguous. By the way, if you have any questions during the lectures, please free to interrupt me and ask. So how to actually deal with this one if we want to send this row? Simplest example would of course be that, okay, we actually just take one element at a time and use several send and receive commands. However, that's not very efficient one. First of all, every time you make an MPI call, you introduce some overhead, there will be some latency in the communication between starting to receive and finalizing to send. So it's not very efficient one. Second, the relatively easy approach would be that, okay, we create some temporary buffer. In this example, it would contain just a buffer for 3 elements, and we copy the non-continuous pattern here to this contiguous memory buffer, send that, and later on, when receiving the data, copy back from some temporary buffer. That can be relatively efficient. Programming a bit more tedious, but MPI allows now us possibility also to create our own data type, which would describe this kind of non-contiguous memory layout. And by using this custom data type, it's possible to communicate, for example, rows of matrix in Fortran with single MPI send and single MPI receive calls. It typically makes the program code look more tidy. It will be easy to maintain. And in many cases, the MPI library itself can do some optimizations for the memory access and can make the communication a bit more efficient than you could achieve just by yourself. Yes?
Sorry, why it is more efficient to copy the A, B, C, which are not contiguous, to another array which is continuous there, and to send it? Because the copy you have to do it with a stride in any case. So what is the advantage to copy it to another?
I would say there is really no. I mean, the preferable way to do is by using MPI data types, and that way you can you might be able to avoid this one extra memory copy. But if you consider a case that instead of you create this temporary buffer, instead of doing several send and receive commands, that more efficient. You have a less latency there. You have less send and receive commands, and also in many cases the performance of MPI communication depends a bit on hardware, and MPI implementation depends on the size of message you are sending. So there are typically larger messages, at least that's up to some certain limit, are more efficient. And especially, okay, for what you are sending 1 or 3 elements, probably doesn't make a big difference. But let's say the dimensions of matrix would be here 1,000. Making 1,000 send and receive calls, or just single send and receive call with continuous buffer, there is clear difference in the performance. Very sort of equivalent situation would arise if you're working in C and would like to communicate instead of row column there, because okay, C would have very much the same pattern there. The user-defined data types in MPI, they use the elementary data types as building blocks. So they typically always sort of consist of predefined MPI data types. And as I've already explained, they allow now communication of non-contiguous data with single MPI calls. We won't be actually discussing how to communicate heterogeneous data with user-defined data types, but that's something you can also do. And I hope that based on the introduction to communicating non-contiguous memory, you can also look at other resources in web or in books how to actually communicate these heterogeneous data.
I have a question.
Yes?
Can you send pointer to functions with MPI? How? Well, I'm asking if you can.
Of course you can send, I mean,
It didn't appear in the
pointer itself, I mean, is something that you can naturally send, but if you think that you would sort of like to communicate the actual function,
yeah.
I would think that it's probably not possible. In principle, you can communicate any sort of contiguous or also non-contiguous byte streams, but I don't know how can you actually sort of convert the function in in C the sort of byte stream that you could communicate with the MPI. If you would be using Python and MPI bindings for Python, which are sort of add-on package and not within the official MPI standard, there it's actually possible to communicate practically any Python object, including functions, with the MPI. But with C, I don't think it's possible. These user-defined data types, they are also sort of essential when wants to do parallel I/O with the MPI I/O, which we'll discuss in the second lecture today. These user-defined data types, they can be used both in point-to-point communication when using MPI sends and MPI receives, but they can also be used in collective communication. I would say that most typical case is in point-to-point communication, but there are some cases where also collective communication with user-defined data types might be useful. And sort of the essential thing to remember about what these data types really mean is that they, when you issue MPI send command, as I said, at the send buffer, in principle, you are just passing memory address there. And in addition to this memory address, the MPI data type instructs where to take the actual data in relation to that memory address. Yes?
I'm not sure if slightly related to a previous question. If I have, let's say, a 2 GB matrix.
Yes?
That's a very large message size, right?
Yes?
So by using this user-defined data types, I can instruct the way that I break it off. I mean, I can give a smaller message size to break the data off by using the data type. And then, when I'm doing the MPI send, I don't have to. I mean, I can define it once and for all in the header of the code or something like that, or is it totally not useful for this purpose?
I would think that if you really need to communicate the whole matrix, if it's very large matrix, might be really that in order to save some MPI internal buffers, you might want to do the communication in PCs. And with user-defined data types, you can actually sort of, we'll discuss that in a bit later, you can communicate directly sort of subblocks of matrix. So that's something you could do. It's still probably not the most typical use case. More typical use case might be that we have, for example, some let's think we have some two-dimensional grid. Have any? Some two-dimensional grid, and we have some sort of hello exchange. There are some coast boundary layers. For example, we have some different stencils. Let's say we would have a second-order stencil. That means that in the boundaries we would need to communicate sort of 2 by matrix dimension sized blocks, and by using these user-defined data types, we can do that by sort of single send and single receive calls. But the sort of important message here is that data type tells where and how to take the data when sending, and where to put and how when receiving. So let's see a bit how we are actually using them. In my lectures, I will use some particular way to present syntax. So for most MPI calls, I will present only sort of pseudocode version, which is very similar to the C function call. And at the end of the lecture material, you should have the sort of real function interface both in C and in Fortran. And I'm not actually designating here the actual data type, but you can see also that all the sort of input arguments will be given in red, output arguments in or parameters in blue. Some of the slides, if you look in the PDFs, have this sort of yellow sign here, basically mean that there's sort of extra material I won't be discussing then during the lectures. So the way to actually use this or create these data types is that we start from some existing one. In most cases, it's some of the predefined MPI data types. In principle, you can start from predefined MPI data type, create your own data type, and use that later on building block as a new data type, but we won't be discussing that. We'll discuss some special routines for different types of memory patterns we want to do. So there will be some routine to actually, or sort of creating the data type. And before it actually can be used, it has to be sort of registered to the MPI system by MPI type commit function call. So we'll always have some data type creation routine here. Then we commit the data type, and after that, we can start to use that in communication. Typical use case is that you do this creation in the beginning of the program, and when you're no longer using the data type, it consumes some internal resources in MPI, so it's a good idea to actually free the data type. If you are just creating the data type in the beginning of program, okay, it's not such a big deal. Still good programming practice to free when it's no longer used. But especially if you're creating the data types within a function calls, within a program blocks, it's a good idea to always decommission that when it's not needed. Here is some list of different data type constructors. We'll be discussing in more detail MPI type vector, type indexed, and type create subarray. The most simplest one is you can actually create the data type for contiguous memory access. That's in practice just the same as using the predefined data types, but and using the count argument when sending and receiving. It's just that sometimes you can make the code a bit cleaner if you define contiguous data type. You can use then always MPI send and receive, where you are sending only sort of one element corresponding of certain data type instead of several ones. And the type create struct here is the most general one. So if you want to communicate heterogeneous data with user-defined data types, this is something that you would be using. So let's look the sort of second simplest ones called MPI type vector. And what it does, it principally basically corresponds to case where we have equally spaced identical blocks of data. So let's say that this would be sort of type of data we have, and we will have to communicate so that we always take two elements, then skip one, then take again two elements, skip one, and so on. In practice, how you can sort of interpret that is that, okay, we are always accessing the data in strides of 3. So we start somewhere, take amount of data, and corresponding to previous starting address, skip 3 elements, and then do it again. So when we are constructing this type of data type, we first specify that how many of these blocks we are going to have. Then we are going to say that, okay, what's the length of single block? In this case, it would be 2. And we give then what's the stride. In this case, it would be 3. And finally, we give the sort of variable new type. Yes?
Is there any effect of little endian, big endian, in, like the two computers communicating, having a different arrangement of bytes?
If you are communicating with two computers with different endianness, MPI library should take care of the endianness issue. So what is sort of one reason to have this old type here and not just specifying number of bytes, for example, that always take, or a single element would be 8 bytes or so, is that you specify here that, for example, that it would be MPI integer, and then the MPI system itself would know that, okay, now in the sending computer, the one element here would be sort of integer, let's say in little endian representation. And now if the receiving side would have a clearly different architecture, then the MPI system would do the proper conversion. In most practical cases, you are working with computers with same architecture. I have never myself worked in a sort of system where you really would have different endianness in two different MPI processes. But in principle, MPI libraries would take care of that issue. Yes?
There are means like between blocks, and there is one like null block.
Yes.
Can we insert it like as necessary, or it's like?
It just means that if this represents now the sort of contiguous memory segment of some data, now when we are sending, it means that by defining this sort of data type, 3 blocks, block length of 2, stride 3, that when we would start to, for example, send from this point, this would be sort of skipped. So MPI library itself would pick first 2 elements, skip 1, then pick second 2, skip 1, and so on.
So is it necessary, or it's just for better code or better readability, better efficiency?
It's for the case if the sort of data you would like to communicate would be in memory in this kind of arrangement. And the reason to use this really is that let's say this is not the data you would like to communicate, these green points here. If you're not using any MPI sort or user-defined data types, once again the options are that, okay, let's say we are sending now. We make first one MPI send call, send 2 elements. Then we make another MPI send call, send 2 elements, and so on and so on. And of course, if the count here, if this would be very sort of long array, that would mean very many MPI send commands. And always when you call these MPI communication routines, there is some overhead. And always when you sort of start communication, there is the latency involved there, so performance would be affected. Now what you can do by using the MPI data type, you can actually do that with single MPI call. So there will be just the latency of single send, and also the amount of data you will be sending would be larger. So the sort of bandwidth, which normally depends on the amount of data you're sending with simple MPI call, would be better. Let's look or try to make short demo how the code for using this type vector looks in practice. Is the font big enough? Can you read that also in the back row? So I think well, I can first do that in Fortran. So I have here a simple sort of skeleton code, defined 8 by 8 array here. do the MPI initialization here. And then rank 0, I initialize the array in such fashion that element 1, 1 is 11, element 1, 2 is 12, and so on, just to make it a little bit easier to see that what's going on in the communication. And in all the other ranks, I'll put the values to 0. And let's say that, okay, now I would like to communicate rows of this array. First thing, we have to declare variable for the MPI data type. In Fortran, they are like most of the MPI sort of special data types. They are integers. Let's call it now row type. So I'll be sending rows. And then for actually creating the type, okay, we have now 8 times 8 matrix we are communicating. So each row will have 8 elements. So we are sending sort of 8 blocks. And now, if we think of the sort of memory layout here, it's always sort of 1. The block length is 1 here. So we put that 1. And the stride now would be the sort of what's the size of the column here. So in this particular case, that would also be 8. If instead of 8 by 8 matrix, this would be, let's say, 6 by 8 matrix, so we would have 6 rows and 8 columns. This would be 6, this would be 8, and so on. And as our array contains integers, the sort of building block here is MPI integer. And then we give the data type, or the newly created data type, and finally the error code in Fortran. Then we commit the data type like this one. So now it's sort of ready to use, and we can use that in communication purposes. So because we initialized the data only in the rank 0, let's do the send from here. So we are sending from array. And now, as we are using a user-defined data type, the sort of number of entities we are sending will be just 1. And it's now this row type here, so the data type that now tells that actually we will be sending 8 integers. So this tells us now that, okay, take the array and make one send corresponding to this row type, which consists of 8 integers, which are taken from this array in blocks of 1 in strides of 8. Yes?
What happens if I want to send just a third row? Is there an option to do it this way?
Then I would just put here that, okay, let's start from third row. Or actually, I think in Fortran it can make temporary copies, so probably you should put something like this one here. But that would now, we can actually look for that. Let's now just first send the first row. We'll send that to rank 1, put some tag there, 11, use MPI vault and the error code. So now we will be sending 1 row of the matrix. And I'm not going to run this more than with 2 CPUs, but let's still put this. It's only rank 1 that will be due to receive. So we'll be receiving to array. We'll be receiving sort of one entity, which is described by this row type. Receive from 11. We won't be interested about the status, like this one. So this is basically now the communicating, sending and receiving one row of this matrix. And here I just have some printing out of the result for the rank 1. Let's see if I made any mistakes here. That's now just because of PI. For some stupid reason, breaks the rows even if I don't want. So let's put the continuation mark there and try again. And of course, for the type commit, I removed the error code here, which okay, it compiled. Let's try to run that with 2 processes. And we can see now that for this rank 1, we received the sort of first row. We can try to do the thing for the third one also here. Of course, we can put here that, okay, let's take the starting point here, the third one. And we can see that, okay, we will still receiving to the sort of first row, but the actual data we obtain is now different. And we could, of course, in the receiving side, also say that, okay, let's receive, for some reason, we want to receive the third row to fifth one. And we can see that, okay, now the data arrived at this point. In C, it would be otherwise more or less equivalent. The only difference is that I won't be doing the sort of whole coding. That in C, sort of data type or type of data would be MPI data type. And here we probably would like to do something like called column typed for sending columns of matrix. And the sort of number of blocks, block lengths, and strides would be just the same as in the Fortran example. Do you have any questions about this very sort of simple sending and communicating of equally spaced non-contiguous data?
Can we have your files?
This example, you will be doing that in the exercise session, so you have the skeleton code there, so you don't have to create the matrix, you just have to create the data type. But you will have also the model solutions there, which of course I suggest that you first try yourself and then, okay?
I have a question about what's going on behind it, not about the syntax. I understand correctly, all the sending and receiving here is by reference.
Yes.
But if I have a cluster and let's say in one core I have memory here and I'm sending to somewhere else, how is what's gets sent? If only the reference, then how does it hold values?
Okay, how it works that you pass reference to the MPI function call. But then what happens in the MPI function call is that once again depends much on the MPI implementation and whether you are within a node and whether the sort of hardware supports some direct memory access or so. But sort of simplest case, you can think that, okay, you make the MPI function call, you pass a reference or pointer in C to the routine. So what actually happens in the MPI call is that it creates some temporary buffer by itself, by the MPI system, and then copies the data from the reference you have specified, and according to the rules of the data type you have specified, and then sends the data in this temporary buffer, and not just the sort of reference, but the actual data. And in the receiving side, MPI first creates some sort of temporary buffer where you actually get the data, receives the data, and then in the receive call, once again, you have passed the sort of reference, pointer, or memory address, and the data type, and the MPI system will do the copying. Whether it does some simple memory copying or some more, let's say, advanced stuff, try to optimize the memory access, so it's really up to MPI implementation and something that user really cannot control. Okay. So that was type vector, the sort of simplest non-trivial MPI data type. Let's look at the next one, which is a bit more complex, and that's now MPI type indexed. And the difference here is that now in type vector, all the blocks, they had the same size, same number of elements, and they also, the strides were always equal. Now with the MPI type indexed, the size of blocks, they can be different, and also the sort of strides or the displacement, they can be also different for different parts of the data. So the first one here, that's just the same how many blocks we have as in MPI type vector. But now, the second one, instead of being single array, it actually now, instead of being single scalar, it's now actually an array. And the size of array should be same as this count here. And similar to the strides, we have now here this displacement. Once again, it's now instead of single scalar, it's an array having same number of elements here. And then we have the sort of building block here, the old data type, and new type here. This would here describe sort of the index type that the first block would contain 2 elements, second one 3, and last one only 1. So the block length would be 2, 3, 1. And now it's actually not, it's really not the stride which we give here, but it's the direct displacement from the beginning. So the first block here, we start from beginning, it's 0. For second one, we start from sort of third position here. So we keep 3 here. And for the last one, now it would be 8 elements here before we start that. So here this displacement, they are really now measured from the beginning of the sort of data structural array. Next slide, I have one sort of practical example where this kind of access pattern might occur. So let's see, we have a square matrix here, and we would like to communicate only the upper or lower triangle here. So this now naturally means that, okay, we want to communicate this data here. It naturally will be non-contiguous in memory, and consists of blocks of different sizes with different displacements. So first one here would be just the sort of dimension of the matrix. Second block would be 1 minus that. I see that I'm missing a minus sign here at this point. Second one smaller, and so on and so on and so on. Also, the displacement would be that, okay, we start from 0 here. Then we would have the sort of size of row plus 1, size of 2 rows plus 2, and so on and so on. So within the loop here, we can evaluate what are the block lengths and displacement. After that, we can create the data type here. You can see that in this case it would be 100 by 100 matrix. So actually, send this by hand would require 100 MPI calls. And after sort of creating this data type, we can communicate the whole upper triangle here by single MPI send call. Any questions about MPI type indexed? So the underlying idea, I hope it's getting you clearer and clearer. We always sort of specify some reference point where to start communicate, and then by the data type here, we specify the actual pattern in memory, where to actually take the data when sending, where to put in receiving. So in this case, it would say that, okay, for this sort of type array, start take data, take this, and do something internally to get that data and communicate.
So can you just repeat again?
Yes.
The variable block length, what was the mistake?
There should be minus sign here. So if you think that, okay, the sort of first block here, it's 100, second one would be 100 minus 1, and so on. The final type, or type creation routine, I will discuss here in more detail, is type create subarray. And that's something that we can send sort of blocks of arrays. Simplest case, of course, would be that if we have a sort of two-dimensional array and would like to communicate certain other smaller two-dimensional blocks from that, but this can be actually generalized to arbitrary dimensional arrays, or maybe limited by the foreground's internal limit. So the idea is here that, okay, first we specify that what's the actual, how many dimensional array we have here. Then we specify which is sort of the full dimension of the array we are referring here. This is now naturally, once again, it's array. Dimension is the number of dimensions. And then next, let's say that, okay, we have a 4 by 4 array, and we would like to communicate the first 2 by 2 block from there. So this would be 4 and 4. And this would be now that, okay, we want to communicate 2 by 2 subblock. So subsizes here would be 2 and 2. Offsets tells us now that what is the starting point of subarray. If we would like to send really the most left upper block of the 4 by 4 matrix, this would be 0 and 0. But if we would like to, for example, take that, okay, let's start from second column, second row, take 2 by 2 subblocks starting from there. This would be 1 and 1. Order is sort of now, because Fortran and C use this different storage order, column major in Fortran, row major in C. And I guess main use for this is that if you would have sort of program written both in C and in Fortran languages and communicating from C part to Fortran and so on, here you can specify that how the matrix is actually is it ordered according to the C rules or Fortran rules. So in most cases, if you are just working with single programming language, if you are working with C, you always specify there MPI order C. If you are working in Fortran, you specify there MPI order Fortran. Yes?
Can be used to transpose the method almost automatic. Basically, if you are running the program in C and the source specifies they want to use a Fortran ordering, and
Yeah. Yeah. That, yes. Yeah, I think that actually what would happen if you send something in Fortran ordering and receive it in C, it would give you the transpose. Here we can see sort of in actual C code example. So let's say we have here some 5 by 5 array, and now we really are wanting to send 2 by 2 or communicate 2 by 2 subblocks from that. And let's say that, okay, this is sort of the part of the matrix we want to communicate. So these are now the sort of offsets here. Here is just some sort of initialization for the array. And then we create now this data type corresponding to this part here. And after committing the data type, we can give the address of the first element here, one entity of this kind of subtype, and also sending here. And as a result, after the receive, rank 0 would have this sort of data. If we would like to, instead of taking this block, take, for example, this block here, still 2 by 2, we would change the offsets here, the starting points here. So this would be 3 and 3, I think. And if you would like to communicate larger than 2 by 2 subblocks, you could also put that there. And really, by one single MPI receive and one simple MPI send calls, we can achieve the communication of certain subblocks of data there. Any questions about SUBARRAY creation at this point? Okay, good. Here's still sort of illustrative examples how to use this. As I mentioned, typical use case for this kind of SUBARRAY would be that, let's say we have 2-dimensional grid, some stencil operations which require some hello exchange here. So, for example, we would need to communicate this part of array, or this, or this, or this. We can create types, SUBARRAY types, corresponding to these different layers here. And then for the actual communication, we can use these sort of defined types for actually exchanging data here. So we always, in principle, just can give the whole array here, one entity, and then the data type there tells that in sending and in receiving that where the data should be taken and where it should be put. So no sort of manual copying here. would be needed, or several send and receive calls. All the examples now have actually utilized the same data type, both in sending and receiving, but that's not actually necessary. You can very well, for example, do the send in contiguous manner here. We can use a vector type here, but then if you just need a single row, we don't need it in matrix. We can actually very well receive that in a contiguous manner. So in the receiving side here, we would have just sort of normal array and n elements of that. Of course, the number of elements here in the receiving side should match the number of elements in this data type here. So the amount of data to be sent and to be received has to be matched, but the data type doesn't have to be the same. It has to be sort of consist of the same data types. So this is MPI floats, this is MPI floats, but you can really do from non-contiguous to contiguous, or actually vice versa. So we can send to contiguous manner, just n elements of floats here, and receive that in non-contiguous manner if needed. As a sort of last thing, a few words about the performance. I think one important aspect of performance is always the performance of the programmer. So especially how easy it's maintain a code. It's sometimes very easy to write a piece of code in a couple of days, but then if the code is something that will be used for next 2, 5, maybe 10 years, it's also very important that the code is sort of easy to understand and maintain. And in my opinion, using the user-defined data type always, or practically always, improves the sort of readability of the actual communication routines. So there is practically always some performance related to the programming and maintaining the code. For the actual wall clock time and so on, benefits are, as I've been saying, that okay, overheads, latency, and so on will be improved because of instead of several send and receives, one uses only one or few sends and receives. Messages are larger, so the bandwidth might be better. And depending or compared to sort of packing and unpacking the data yourself, MPI can sometimes do optimization for the memory access. Typically, the more sort of complex data type, the more overhead from the sort of data type creation and usage there will be. So it's always good idea to use the simplest possible data type. So if you're sort of sending rows of matrix, in principle you could do MPI type subarrays. There, one of the subsizes would be 1. But for performance reasons, you should use the simple possibility, which is the MPI type vector. It really depends also on the sort of MPI implementation and hardware. But as an example, sending a row in C code on quite recent gray XC machine at CSC of 512 dimensional matrix. If you do that with sort of multiple sends, takes 10 milliseconds. If you do manual packing, we can do 10 times faster. And by using the user-defined data types, we get more or less factor of 2 improvements still there. Yes?
If you want to send an array of complex objects, like a class that has double and integer and all sorts, what's the fastest way to do it? Just send them all as complex objects, or decompose them into an array of each of the primitive types?
I haven't actually done the benchmark for this case, for example, in this machine. The last time I tried that, I think at the end the fastest manner was to sort of use MPI byte type which means that, okay, send some bytes, and then calculate that what's the actual size of the structure in bytes that you won't be sending. It would be sending also some, let's say, padding and so on, so unnecessary data. But at least that's probably some 2 years ago, I think I tried this benchmark. At that time, using MPI byte was clearly faster than using the type struct. Situation might be changed, and it probably gives you a bit easier programming if you use the type struct. But for performance point of view, if you have a really complex data structure, sending everything as a contiguous byte stream might be the most efficient one. Of course, that requires that you will be working with architecture where all the nodes have the sort of same representation for the number, but that's in most cases true. So there you of course won't have the possibility, or you have to do everything manually if you have a little endian in one side and big endian in one side. But as I said, that's not very common use case.
So the byte is some bitwise is faster, but it's not compatible with all visual.
Yeah, something like that. But in practice, I would say it's compatible with 99% of machines. Okay, that's. Sorry.
Those times seems to be too long.
It's it's not a single sense. So I think I did several sense there. So it's just sort of I think probably 100 cents or something like that to sort of get a bit more statistics and so on. Sort of important thing is the relative magnitude there.
So it's not for a single row, maybe it's on the whole matrix.
Well, it's sort of sending the single rows several times, or something like that. Yeah, so probably scale, but then by the number of cents. So I think this more or less brings me to summary. So user-defined or derived data types in MPI allow communication of non-contiguous memory segments. Most archetypical example is probably communicating a row of matrix in Fortran or column of matrix in C, but there are also some other very common sort of memory patterns where the data you want to communicate is not going to be contiguous. Sort of reason to use these data types is that they, in most cases, improve the maintainability of the program and also can offer the MPI system optimization possibilities. So you might achieve better performance. Life cycle of data types is always that you sort of create or you define the data type, you commit the system, and when you are no longer using it, you free it. And we discussed a few different constructors that MPI provides. So in one of the slides, there are also a few more of them, but these are probably the most useful ones. Do you have any questions about using the data types at this point? Okay, so I think it's always best way to learn something is to get your hands dirty with that and do some programming yourself. So there are some exercises you could now try to do. So first, I think you should just try to do the same example I did by saying a row if you're a Fortran programmer or column if you're a C programmer, trying to use both the manual packing, unpacking, and predefined MPI data types. and then continue with the SUBARRAY data type, and maybe try, if you have time, apply that for a simple two-dimensional heat equation. So if you go to the course web page, you should find some skeleton code there, so you don't have to do all the initialization and so on. And most of the code pieces, they should contain some commented segments, begin to do, end to do, which sort of designate that which part of the code you should be working. And you will find also the sort of my ways to solve the problems here, which, as I said, I suggest that you still first try to do exercises yourself before looking for the model solutions. And I guess you have been doing some basic MPI exercises yesterday, so I hope you're all already familiar how to access some system where you have MPI installed and how to compile and run simple MPI programs.